A fan motor that feels hot is giving you evidence, but not a diagnosis. Overload, bad power, blocked cooling, bearing drag, high ambient temperature, and repeated starts can all create the same symptom. Here is a fast way to separate them. Treat the motor as a heat budget. Copper, magnetic, switching, bearing, and friction losses put heat in. Airflow, the housing, and the mounting structure take heat out. Temperature rises whenever heat arrives faster than the system can reject it. First, make the reading comparable. Record the exact measurement point, method, load, current, speed, cooling air ambient, airflow, and elapsed warm-up time. Use the motor nameplate, insulation system, protection settings, and manufacturer limits. There is no single safe surface temperature number for every motor. 'Cause one is overload or the wrong operating point. Compare actual current with the applicable rating, then check speed, airflow, duct restriction, wheel condition, and driven load. High current confirms excess electrical loading. It still does not tell you which mechanical or aerodynamic demand created it. 'Cause 2 is the supply or drive. Match the test to the architecture. On a 3-phase motor, compare voltage and current by phase. On a single-phase or electronically commutated unit, follow its specified input and control checks. Loose or high-resistance connections can create localized heat. 'Cause 3 is lost cooling. A blocked inlet, dirt on cooling surfaces, stalled external fan, or recirculated hot air reduces heat rejection. Isolate all energy and verify zero energy before opening guards or reaching near rotating parts. 'Cause 4 is bearing drag or another mechanical load. Compare bearing area temperature with the housing, listen for changed noise, review vibration, and check shaft movement only in the safely isolated state. Fix alignment, lubrication, belt tension, rubbing, or the driven load, not merely the temperature symptom. 'Cause 5 is the environment. High cooling air temperature, poor enclosure ventilation, hot air recirculation, or operation outside the allowed altitude in ambient envelope consumes thermal margin. Measure the air entering the cooling path, not a convenient room location. 'Cause 6 is duty. Frequent starts, long acceleration, aggressive cycling, or prolonged low-speed operation can accumulate heat faster than the motor cools. A thermal protector reacts to that heat. A trip is evidence of the thermal state, not the root cause. Now build the matrix. For one repeatable operating state, record ambient, current, speed, airflow, bearing condition, and duty history. The pattern across those measurements is more useful than one infrared number. Correct one cause, restore every guard, and repeat the same run at the same load, point, and warm-up interval. A lower, stabilizing trend is stronger evidence than a cooler reading taken at a different condition. Efficient motor and control design can reduce losses, but only when correctly selected, applied, and validated. So the sequence is, make the state safe, reproduce the condition, measure consistently, test load and supply, inspect cooling and mechanics, review environment and duty, then verify the correction. If you want a root cause review, send the motor model, supply or drive, current by phase, ambient, airflow, duty cycle, and temperature trend.